Hi, so welcome back. So we'll now talk about typical supervised machine learning setup, and this, in my opinion, is the most important module of the course. Of course, as we go along, I'll say this for many modules, but I think this is the most important one, right? So please pay attention. So this is what we have, right? So we looked at the sigmoid neuron, and we looked at one particular function within this family, which is the logistic function. Now what next, right? So we have seen this, right? So what was our pattern when we had introduced perceptrons? We saw the perceptron model, and then what did we do? Where did it go from there? We first looked at the algorithm for learning the weights, right? So we want the same thing now. I've defined this, but now how do I learn the weights? That's not clear, right? So I want to have an algorithm which can learn these weights. But before I had done the perceptron learning algorithm, I had taken a slight detour and spoken about errors, right? Because that was important to understand the error, because the whole point of the algorithm was that whenever you make an error, you do some correction, right? And that's why understanding error was important. Here also there is something similar. So I'm going to revisit the concept of error again, and then from there start working towards the algorithm, right? So, but in this video, we'll not do the algorithm, we'll just do the machine learning setup, right? So let's look at that. So going back to the perceptron algorithms, I had seen these kind of data distributions there, and I had said that this is not linearly separable. Of course, it is not. And we had said that a single perceptron cannot deal with this data, right? Or cannot deal with not linearly separable data. But what do I mean by cannot deal, right? What would happen if I apply perceptron algorithm? Suppose I blindly go and say, okay, I want to just apply the perceptron algorithm here. What would it do? Right? Can you tell me what would happen in this case? It will make errors for some points. What's the point of a perceptron algorithm? The idea of a perceptron algorithm is that it will find some separation boundary, right? Now we know that if the data is not linearly separable, it will not converge, right? Because it will keep toggling, some points will be here and there. But if I just do, okay, I'll just do it for some 1000 iterations. For a fixed k, I'll do it. So what do you expect would happen at the end? It could draw some line, right? And there are many lines possible. It could draw this, many things, right? So what do you think is a possible line here that it would end up with if I just ran the perceptron algorithm? Just think about it, okay? I mean, it's hard for you to tell me what you're thinking, but just think about it, and then when I show you the answer, just see whether you are in agreement with that. Sorry? Somewhere in the middle of the data, and we all understand what he means by middle of the data, right? So let's see. So this is what it would do in the upper case, right? Where most points are, I mean, there are errors. I mean, that's a hard problem given. It cannot really separate by a linear boundary, but it will draw some boundary, right? In the second case also, it will draw some boundary. And here the situation is better. As you can see, it's making an error on some 3 orange points, which are getting classified as blue, and maybe a couple of blue points, which are getting classified as orange, right? And in most real world applications, we could deal with this kind of an error, right? So there are like maybe 10 blue points here, of which 2 are wrong, and 10 orange points, of which 2 or 3 are wrong. So 20% error we could deal with, unless this is like a mission critical application, in which case it might be difficult. But in most real world applications, we might be okay with it, right? For example, if you're predicting whether this person is likely to vote for one party or the other, and if you make some error in that prediction, like 20% of the people you predict wrongly, it won't make much of a difference, right? So it would still give you some rough idea of how the election is going, right? And in many cases, of course, unless it's a very closely fought election, but in most cases, if the error is around 5-10%, you can live with it, right? So from now on, we are going to live with this idea of error, that error may not always go to 0, and our goal would be to just minimize the error as much as possible, right? So if I were to actually have a 0 error here, I would need something very complex, right? So I would want a decision boundary, which perhaps, I don't know, looks something like this, right? And now even that is not enough. Yeah, I just want an island here, right? So it's very difficult, right? I mean, it's like a very complex boundary, so that all the blue points are separated from the orange points. And we will be okay if at least I can find some boundary, right, where the error is as small as it can be, and I can live with that little error, right? So that's what I'm going to do. I'm going to now start using the term minimize the error, instead of saying that the error should be 0, right? So that's one switch I'm going to make, right? And now with this background, we are ready to discuss what a typical supervised machine learning setup looks like. Not machine learning, but supervised machine learning, right? So always given some data. Okay, what is this data? This is some Rn, right? These are vectors belonging to Rn, okay? And this is some, let's for the simplicity assume that it's just a real value. It could again be a vector, right? It could be the case that given the data about a movie, I'm trying to predict the box office collection of the movie. I'm also trying to predict the IMDb rating of the movie, right? So I could be predicting two things here, right? But for now, I'll just assume that we're just dealing with a real valued output and not a vector, okay? Now, we have already seen what this data also could look like, right? So, and this is where the most important part comes in. Let me just quickly go ahead. Okay, this is not what I want to do now. So, this we have seen application, right? So, let me just define all of these, right? So, these are my x's, okay? This is a vector which belongs to R. Let me just call it M, right? Because I'm using N for something else. And I have N such data points, right? So in my, I have N such data points. So in my oil mining case, I'm assuming that there are already N drilling stations set up somewhere and I have all the data about them, right? What was the pressure, what was the salinity, these N points by which I am defining a location or characterizing a location, and I also know the Y for them, right? So I have a M dimensional input, I have a single dimensional output, which is the amount of oil mined for them, and I have given some N such training points, right? So this is what a typical machine learning setup looks like. Similarly, if I look at the other example where I had the credit card or maybe I had the bank interest rate that I wanted to decide, right? So I have the past history of the person, and this history is being characterized by various things. What is the salary of the person? What is the education level of the person? What is the family size of the person? Does he have any past loans? What was the interest rate on the past loans? How soon did he dispose of that loan, and so on, right? So all of those are the past history, and based on that, for my existing customers, I know what was the rate at which it was suitable to give them, right? And now this training data is given to me, and there are n such training points, each of which is m dimensional, and I'm trying to predict a real valued output, right? And now you can think of on and on of so many such problems, right? So all the machine learning, supervised machine learning problems have this form. I'll give one more, which was the movie prediction problem or the box office collection problem, right? So I want to predict the box office collection of a movie. I have data about the movie, right? What was the budget of the movie? How many superstars are there in the movie, right? How good, who is the music director of the movie? Who is the cinematographer? All of this I will have, and based on past movies, I know what is the box office collection, what is the genre of the movie. All of this is there, right? And I know this. So now I've given such many such movies from past and such movies. I'm characterizing each movie by an m-dimensional vector, which is some inputs about the movie, and I want to predict the box office collection, right? So this is what the data part looks like, and the main point here is that across all supervised machine learning setups, this is what it looks like. Every machine learning problem, you can cast it into this matrix where you're given the x's and the y's, and you're given many such x comma y pairs. Okay. Now, this is where now the challenge is, right? This is what the crux of machine learning is. So we have a y, right? And we have a reason to believe that this y depends on the input x, right? So what is the y here? The box office collection, and it depends on the characteristics of the movie, right? This depends. This equation is still not complete. Y is equal to x is not what I want to write. I want to write something else, but I'll come to that, right? I'm saying that y depends on x. Then similarly in the interest rate, y depends on that, all the inputs that I'm taking, and even in the first example of oil, it depends. So what's the mathematical way of saying that something depends on something? Y is equal to a function of x, right? So I would say that y is equal to f of x, right? Now, if I knew this f, there's no problem in the world, right? If I knew what is the function such that I plug in the values of salinity, pressure, density, all of these factors, and it just tells me what the y would be. If I had such a function, all of us would be billionaires, right? We will just look at different locations, plug in those values, and wherever we get the highest mining, we'll go ahead and set up drilling stations there, right? But that function is not known, right? So this is the beauty of the problem. We know that a function exists. The output has to depend on certain inputs, right? These are the inputs. And you could argue about, oh, but maybe you have not considered all the x's. I would argue by saying, okay, consider all the x's. If you have forgotten to consider the parent salary, okay, put it in. You might say that it would depend on the parent salary. You would say that it would depend on the children's education. Okay, put all of that in, right? And construct as comprehensive an x as you can. And then I would say that the y depends on this x. Right? So y is a function of x. So that is known, that y is a function of x. But what is not known is what is this function. So now what do you do in this situation, right? So you want to now, your goal is to come up with this function so that for new x's, so for a new location, which say the Shell company has hired you and said, okay, this is the location I'm considering. Can you tell me what is the oil that I could mine from there? So you want to plug in that here and tell the company that this is what the quantity of oil I estimate, right? So you want to do that. So what do you do in this case? And this is the crux of machine learning, that you assume some function, okay? You assume there is a function x parameterized by some parameters w, or more generally we call it theta also at times. So I'll just use theta maybe, okay? So you assume some form, and that assumption is up to you, right? You assume that there is a function f hat which relates the inputs to the outputs. It has certain parameters, and now your job is to learn these parameters from the given data, okay? Now, let's look at a simple case. So, let's suppose you assume that y is equal to wx plus b. This is a function, okay? And you have assumed that y depends on x, it's capturing that, and you have some parameters. Now, how would you estimate the values of w and b if I give you 2 points? Maybe I should use a different form, which is y is equal to mx plus c, and now you would remember from high school that how do you estimate m and c? If you're given 2 points, you can get these two simultaneous equations and then you can find the values of m and c, right? So that is how you could do. Now, in real world applications, it won't be like, I mean, I've taken a very simplistic example, but what would happen is that you'll be given many such data points. The key takeaway from the example is that if you're given data points, which was 2x comma y pairs, right? I have n x comma y pairs here. If I just had 2x comma y pairs, then I could predict the values of w and b, right? I could find out the values of w and b, right? And from that, I just want you to extrapolate your belief and say that if you have many data points and many parameters, you could come up with algorithms to find the values of these parameters, okay? In this case, our algorithm was simple. Let's just construct a simultaneous equation and solve that simultaneous equation, right? But you could extrapolate this idea and you could say that if you have many data points given to you where the values of y and x are known, and now you have some parameters to find, you could estimate these parameters from the data. Okay, so that's the game in machine learning. There are a few more details. I'll now erase this whatever I have here and go into those details. Okay. Okay. So our approximation of the relation between x and y is called the model, right? So when I say that I have a machine learning model, what does a model mean? Model means your belief of what is the relation between y and x, right? And it could be anything. It could be this function. We just saw this. That y, does it satisfy the criteria that I have? Y is a function of x. It also has some parameters, okay? What is this? Have you seen this before in machine learning? In machine learning, what is this called? This is called logistic regression, right? This is the logistic regression model. What is this? Linear regression. You are assuming there is a linear relationship between y and x. This is, you are assuming there is a quadratic relation, right? Any of this assumption is equally good or bad, right? Now in deep learning, you're going to, we'll see that later on. Again, you assume some f, right? And as the name suggests, this f is going to be very deep. What it means in mathematical terms is going to be a very complex composite function, right? And we'll get there. But again, in deep learning, there's nothing different. It's just that as you had certain forms of f hat here, deep learning has a certain form, and that form we will see later as we go on. Okay. Now one question. So why are parameters important here? Why can't I just assume that y hat is equal to 1 over 1 plus e raised to minus x? Why do I need the parameter? This is also a function. Y hat depends on x because this is a function of x. Why can't I use this? Why am I complicating it by adding parameters? Different different weightages to different features. Okay, but something more fundamental than that, right? I mean, okay. So doing this is akin to saying that y is equal to 3x plus 2. I've fixed my parameters, right? Here I'm just saying that the parameter is 1, right? What is the problem with this? I'm not learning this. I just said, okay, y is equal to 3x plus 2. I just cooked it up. Now, who tells me whether 3 and 2 are the right values? I have to learn that from the data, right? So if I don't have any parameters, I have nothing to learn. I just told you y hat is equal to 1 plus e raised to minus x. Now throw away all the data that you have. For any new x that you get, just plug in here and you will get the value and live with whatever value. And that's not what you want to do, right? You want to have certain parameters so that those parameters can be learned, right? So what would happen in the sigmoid case, for example, right? This is what a sigmoid function looks like, right? And it will look like this S-shaped. But depending on the values of w and b, it will decide whether this is something like this, or is it something like this, right? So all of this will depend on your values of w. So you can have a function form, but you can adjust that form of the function by, or adjust the shape of the function by using these parameters, right? So that's why if you don't have parameters, then all your data is useless, right? If you just say my equation is this, you have not even looked at the 2 points. How do you know that those 2 points will satisfy this equation, right? So you have to look at the points and then come up with this equation, right? Then you have to find the values of w and b. So that's the same idea here. That's why you need these parameters. Okay, now learning algorithm, right? So once you have set up the model, you have the data, now you need an algorithm so that you can learn these parameters w. In the case of y is equal to mx plus c, our algorithm was simple. Just have 2 points, plug them in, get 2 simultaneous equations, solve that, right? So the algorithm is the algorithm for solving the simultaneous equation and we are done, right? But in large parameters, large data, we'll need something better, something more principled. And we have already seen one example, which is the perceptron learning algorithm. And now we are going to see gradient descent in some time, right? So that's what we need. Now, what should the goal of this learning algorithm be? So when would you say that the parameters that I have learned are good, right? So in the case of perceptron algorithm, we had this loop which said while not convergence do this, right? And there we had assumed that the data is linearly separable. So I will keep running the algorithm till no point moves, right? Or till the new value of w does not move because all the points are on the correct side of the line or the plane, right? That was fine. But that means you are going for zero error, right? But now there is no idea of zero error, as I said. In most real world applications, we'll have to deal with minimum error, right? So then what should your learning algorithm do? It should have a certain objective, right? In the case of perceptron, the objective was to separate the data. That means no point misclassified. That means zero error. Now your objective function, which is going to guide the learning algorithm, has to be something about minimizing the error. Right? How to do that, what is error, all of that we'll see in the subsequent slides, right? But that is what the goal be, right? And let's see. Yeah. So the learning algorithm should aim to minimize the loss function, right? There is more to be said here, but I'll not say those things in this slide. We are going to come back to this slide again in a different form, and then I'll say a bit more, right? So right now, I think what should be clear is the data setup, those 3 examples that I showed, the model, which is our approximation of the relation between x and y, the learning algorithm, which whole point is to learn w. Any learning has to be driven by an objective, right? So that objective is to minimize the error function. Right? That's what the objective is. Now, how do you come up with the learning algorithm? How do you define the objective function, right? So up till this point, I have defined everything mathematically, right? But now objective function I have not defined, so I'll have to tell you what the objective function is, but we'll come back to that, okay? So now consider our movie example. So this is the movie data given to me, right? Xi is equal to movie. I'm just using a shortcut. When I say xi is equal to movie, I mean that entire vector, right? All the actor information, budget information, number of superstars, blah, blah. And yi is equal to 0, 1, right? So that's what it is. our approximation of the relation between x and y. So our approximation was that y hat is equal to the sigmoid function of x, right, with the parameters being w. Okay. Then learning algorithm is gradient descent. We don't know that, but the idea of gradient descent is to find the w's, right? And what is the objective function? What should my objective function be, right? Let's try to arrive at an objective function. So I'm given some data, okay, x comma y, and now I have this approximation. At the end of learning, what would you want? You would want that this y hat should be as close to y, right? That means the difference between y hat and y should be as small as possible, okay? For all the training examples that I have, maybe n, right? If I sum up this difference, okay, and I'll just call it as difference, right? So difference between y hat and y, and I can now define the difference, the function, the way I want to, right? So the difference between y hat and y summed across all the training examples should be as small as possible, right? That's the same as saying that minimize this difference, right? So this is my loss function now, okay, and I want to minimize this, okay, and I could choose different ways of defining this distance or the d function, right? And I could choose the squared error loss, for example. So what is this saying? That this is my loss function, which is I look at all the training examples, I look at the difference between y hat and y, and I take the square of the difference. Why do we take the square of the difference? So that the positive errors don't cancel the negative errors, right? So now suppose I wanted the value to be 1, okay, and it predicted it as 0.5. Then my error is minus 0.5, okay. Yeah, this was y hat, this was y. So y hat minus y is minus 0.5. But there was another example where I wanted y and y hat was predicted as 1.5. So now my difference would be 0.5 plus 0.5. So if I just take the sum of the differences, then this minus 0.5 will cancel this 0.5 and it will look like I have 0 error. Whereas actually I have made 2 errors and 2 horrible errors, right? Both off by 0.5. So the moment you square it, that sign disappears, right? So you could take the square, and the other, you could have argued that why not just take the norm, right? Just the absolute value, right? But the problem with the absolute value is that it's not a smooth differentiable function, whereas a square function is a smooth differentiable function. And we want smooth differentiable functions because later on the hero of the course is going to be calculus, where differentiability would be important, right? So that's the idea. So now I have defined an objective function, and the learning algorithm should find w's such that when I plug in these values of w, this loss value that I get should be as small as possible. What does that mean? There are infinite possible values of w, right? So w is an Rn vector, right? It's an n-dimensional real vector, right? M, okay. Sorry, m-dimensional real vector. And these are real values. That's okay. M plus 1, right? That's okay, not a problem. So order m we can say, right? So m plus 1 because w naught is also there. So this is m plus 1 dimensional vector which can take real values. Each value can go from minus infinity to infinity, right? So there are infinite possibilities here. Of those, I want one such w which if I plug in, if I were able to plug in all these infinite values of w into this equation, right? This is the equation that I care about. Then I want that w which will give me the smallest value for the loss function. That's what my goal is, right? So that's the objective of training. Now the other thing that I want to say here, right? I just want to talk a bit more about this learning algorithm and the loss function, right? So any kind of learning, as I said, is always driven by some objective, right? And I like to give this analogy that suppose in high school you're learning trigonometry, right? So when you're learning the chapter, what are you doing? You're reading the chapter because you're allowed to read. This is not a test, right? You're allowed to read the textbook, and your goal would be to ensure that all the formulae which are given in the chapter, you don't make any errors on that. Is that correct? That's what your goal would be. That is akin to saying that for all the training points that I am given, I should not make any error, or I should make minimum errors, the minimum possible errors, right? So that's what training is. Then at the end of the chapter, you have exercises, right? That's your validation set, okay? Because now you have not seen this formula. You have just learned the formula in the training data. But using that, you should be able to solve this exercise. And you might make some mistakes here. So you're again allowed to go back and relearn the chapter, right? You could say, oh, I'm not able to figure this out. Maybe go back and look at this, right? So that's your validation set. And then you have a test set, which is your exam. So now you have done the training, you have done the validation set, again toggle between training and validation, and maybe you have some confidence now. Once you go to the test set, once you go to write the exam, you're not again allowed to do the training, right? So you have a training error, you have a validation error, and you have a test error. During training, what we are talking about is the training error, which means the error on the training data, right? Which is the error on the chapter that you have read, right? The contents of the chapter, you should know everything well, or you have minimum errors, right? So that's the analogy you should keep in mind. Okay. Yeah. So I'll end this module here, and we'll come back and talk about and ways of learning these parameters, right? So let's do that.